So today we are going to continue talking about partial differential equations. And we've discussed the finite difference, finite volume, and today we are going to be starting talking about finite elements. All right, so this is the third method we are talking about in solving partial differential equations. And as I said, the finite volume is really popular in fluid mechanics. Finite element is really the predominant method for structural mechanics. So solving partial differential equations that determines the force, the stresses in like aircraft structures, spaceships, buildings, bridges. These are the kind of domain where finite elements are really used across many different industries. Okay. So finite elements discretizes a function in a very different way from finite difference and finite volume. So we have actually already seen demos of what finite difference and the finite volume does. And today I'm going to show you how finite element discretizes a function. Okay. So this is the same kind of a thing we have been doing for finite difference and finite volume. And if you remember, in finite difference, when we draw a function, what my computer stores is the values of the function at the grid points. In finite volume, I'm storing the average of the function values within the finite volumes. And now let me draw you an arbitrary function. And we're going to show how finite elements is discretizing the function. All right, does everybody see that? So here's the question I want to ask you. Please observe, right, the faint red line which I draw as the original function and the solid red line, which is a finite element approximation of this function. And can somebody tell me what does finite element do? What is the discretization actually doing? This is far less obvious, right, than what finite difference does and what finite volume does. So can somebody take a brave guess of what finite element is doing in this scenario?
Is it taking the average of the slope across each element?
Is it taking an average of the slope across each element? Actually, not exactly, right? So if I'm taking the average slope, then the difference between the left and right of the function should be the same between the approximate and original functions, right? Because if the averaged slope is the same, then the integrated slope should be the same. And the integrated slope, again, according to the fundamental theorem of calculus, the integrated slope, which is derivative, is actually the delta between the left value of the function and the right value of the function. But you don't see that, right? If you observe the first element, you're going to see, okay, the actual function changed less than the approximate function has changed. All right, so very good guess, but like it's not exactly what finite element is doing. Anybody else wants to take a guess? So first of all, when you look at the function, what do you see, right? So in finite difference, we see that it's just a bunch of points, right? In finite volume, we see that it's a bunch of constants. In finite element, what's special about the solid red line?
It looks piecewise linear.
It looks like piecewise linear, exactly. So it is piecewise linear. That's a very good observation, right? It is piecewise linear. Okay, and what else?
Continuous.
It's continuous, right? This is This is actually a very important distinction of finite elements from the other methods. The other methods actually really discretizes the function, right? In finite difference, I mean, we kind of got rid of the concept of a continuous function because we are only concerned with the values of the function on the grid points, right? We just got rid of the concept of function altogether. Well, in finite volume, we're just storing the volume averages. We are almost also got rid of the concept of the function, right? So instead of functions, we just store the averages. Finite elements, we are approximating a function with another function. As you have pointed out, the function we use to approximate is not as general as any function. It is piecewise linear, it is continuous, right? So there is a lot of constraints on what kind of function I can use to do this approximation. But we still end up with a function, right? We are not just removing the concept function and approximate it with a bunch of numbers, be it the value of the function at the grid points or the average of the functions. We still have a function to play with. So that's really an important difference between the other two methods and finite elements.